Okay, so in this video we are looking at gas laws practice number 1, starting with number 4, which is a Charles's law problem. So looking at this first problem, if you didn't know it was Charles's law, we should first go through and label our variables. So it says a gas at 89 degrees Celsius occupies a volume 0.67 liters. So we have a volume and a temperature. Okay, and these are our initial temperature and volume, our ones. At what temperatures, we're looking for a second temperature, a T2, will the volume increase to 1.12 liters? So this is a second volume, our V2 value. So if we were to take our gas law, PV over NT, and then select the variables that we have temperature and volume, so we want an equation that just utilizes temperature and volume. We would get V over T, so V1 over T1 equals V2 over T2. And we'd get the same relationship that is shown up here as Charles's law, which is indeed what we need to use in this problem. Okay, so when we're using Charles's law, there's a couple of things to remember. First of all, our units of volume do need to be the same unit. So in this case, we have one volume, which is given in liters. So our second volume, which is what we're looking for, that'll be X in this case. Oh, no, we're not looking for it. It's given to us. It's also given in liters. So we're actually good here. We have liters and liters. Our temperatures for Charles's law, or any gas law for that matter, before we use the gas law, we need to convert our temperature to Kelvin. So I'm going to make a note of that. Our temperature must be in Kelvin. And we do this by adding 273. So take the degrees Celsius plus 273 will give you Kelvin. So our T1 value, before we use it, we want to convert it to Kelvin. So 89 plus 273 will give us, 89 plus 273 will give us 362 Kelvin. And this is the value that we want to substitute into our gas law. And then when our T2 value comes out of this equation, it's also going to be in Kelvin. So when we get our value of T2, I'm going to put blank Kelvin to remind us that it is in Kelvin on the Kelvin scale. Notice that our answer choices here are not in the Kelvin scale. So when we get T2, we're going to get it in Kelvin, and then we'll have to subtract 273 to get it back to Celsius. But we're getting a little ahead of ourselves here. All right, so let's look at this problem. V1 over T1. So V1 would be 0.67 liters. 0.67 liters over T1. And our T1 is 89 degrees Celsius, but we knew we needed it in a Kelvin, so it's 362 Kelvin equals V2, which is 1.12 liters, over T2, which we don't know, so we're going to plug in X. So to solve this, I'm going to move my light a little bit here to make it a little brighter. To solve this, we want to cross multiply. So we're going to do 0.67 times X will equal 362 times 1.12. So 0.67, I'm going to leave out my units now. 0.67x equals 362 times 1.2. 362 times 1.12. Sorry about that. Okay, and now to solve for x, I need to divide by 0.67 on both sides. So we're going to end up with x sorry, my equal sign wasn't very good there, 362 times 1.12 divided by 0.17. Need some light over here so we can see our calculator. 362 times 1.12 divided by 0.67. Alright, and when I did that, I got 605.13. And that answer is in Kelvin, 605.13. So to convert this back to Celsius, so it matches one of my answer choices, I need to subtract 273. So 605 minus 273 minus 273 will give me an answer in Celsius of 332.13 degrees Celsius. And we're looking for an answer that is very similar to what we got. 332.13 is very close to 330. This answer is just rounded to 2 significant figures. So that is our answer to number 4. Okay, so our next problem is another Charles's Law problem. It says the Celsius temperature of a 3-liter sample of gas is lowered from 80 degrees Celsius, so that's our initial temperature, our T1, to 30 degrees Celsius. There's our T2 value. We have T1 and T2 given. The Celsius temperature of a 3-liter sample of gas is lowered from, so we're starting at 3 liters. This is our V1 value. What is the final volume? So this is our V2 that we're being asked for. So that's going to be our value of X. So we have all our variables labeled, but of course, since this is a gas law that involves temperature, we need to convert our temperatures to the Kelvin scale. So T1 is 80 degrees Celsius, so plus 273 will give us our temperature in Kelvin, and T2 is 30 degrees Celsius plus 273 will give us our temperature in Kelvin. So 80 plus 273 is 353 Kelvin, and 30 plus 273 gives us 303. I really should have done that one in my head. Alright, so now we have our T1, our T2, and our V1. We're looking for V2, and because our V1 is in liters, we know our V2 is also going to be some number of liters. I'm going to go ahead and plug that in up there. Okay, so let's substitute some values into our equation. So, V1 over T1 is going to equal V2 over T2. Our V1 value is 3.0 liters over T1, which we need in Kelvin, 353 Kelvin, equals V2, which we don't know what that is yet, so we're going to plug in X, over T2, which is 303 Kelvin. So here in this problem, we need to use our cross-multiplying strategy. So we're going to do 3 times 303 will equal 353 times X. 3 times 303, I'm going to take out my units and just leave my values, equals 353 times X. So to solve for X, all I need to do is divide by 353, and whatever I do on one side, I also have to do to the other side. So I'm going to be left with X equals 3 times 303 divided by 353. 3 times 303. I'm going to hit enter, get my answer, divided by 353. And that gave me 2.575, and my units are liters. So I'm looking up the answers. 2.575 is very close to 2.58 liters, so that is my final answer. Okay, this last problem is one last Charles's Law problem. What is the volume of air in a balloon that occupies 0.620 liters, that's a volume, at 25 degrees Celsius, that's a temperature. So those are our initials. We're starting at 0.62 liters, 25 degrees Celsius. If the temperature is lowered, so new temperature, T2, to 0 degrees Celsius. Okay, so we have a V1, a T1, and a T2. And so we are looking for a volume, a V2. What is the volume if it's lowered to 0 degrees Celsius? So V2 will be our value of X in this case. So I want to draw your attention to the fact that this problem has 0 degrees Celsius, and this is actually why we need the Kelvin scale, because if we were to use Charles's Law, V1 over T1, so V1, 0.62 liters over T1, 25 degrees Celsius, equals V2, X over 0 degrees Celsius, T2, then the gas law wouldn't work. We would get 0.62 times 0 equals 25 times x. And this would give us 0 on this side. So 0.62 times 0 equals 25x. Well, that doesn't work because then when we divide by 25, we still get 0 as our answer. So this doesn't work. So this is why we have to convert our temperature to the Kelvin scale. This right here is very wrong. This does not work out properly. So I'm going to put a big X through it. Do not do this. Do not use degrees Celsius. You have to convert to Kelvin before you start. And so we're going to do that this time. We're going to do it correctly. So we have T1 is 25 degrees Celsius plus 273 will get us to Kelvin. So that's 298 Kelvin. And then our T2 value is 0 degrees Celsius. So when we convert that to Kelvin, we get 273. Okay, so now we're going to use the gas law with our temperatures in Kelvin, and you'll notice it's going to give us a very different answer, which will be the correct answer because we will have done it right this time. So let's use this gas law again, V1 over T1, so V1, 0.62 liters, 0 liters, over T1, which is 298 Kelvin, equals V2, which we don't know, so we'll plug in X, over our T2 value, which is 273 Kelvin. Alright, so we're going to cross multiply. 0.62 times 273, 0.62 times 273 equals 298 times X. So to get X by itself, we're going to divide by 298 on both sides. And then we're going to be left with X equals 0.62 times 273 divided by 298. 0.62 times 273 divided by 298. Okay, and that gives me 0.5679. 9. We'll round to that point, but you'll notice this is a very different answer than the 0 that we got when we used the Celsius scale. Celsius does not work for gas laws. You have to convert to Kelvin. So 0.56799 in my units. Volume was given in liters. My units here are also liters. Looking at my answer choices, I'm looking for an answer that's very close. 0.567 is very close to 0.57 liters. So A is my correct answer here.